David Smith here with another flipped classroom math video. A few tips before we get started. Remember, you can always pause the video if you need to catch up with your notes. You can also speed up or slow down the playback if that helps. Finally, you can turn on the captions so you can see my words going by at the bottom of your screen. Today we're going to work on some applications of derivatives. Our first example is going to be an economics problem. Before we jump into that, I'd like to review a few terms and concepts for the functions we're going to be manipulating. So check this out. Cost function. That is the function for how much it costs to make X units. You have a function, you put 12 in, we're making 12 units, it's going to spit out how much it costs to make 12 units. Revenue function. This is the gross sales for selling X units. So we want to find out how much we're going to sell for making 12 units. For selling 12 units, we would put 12 in the revenue function. And that would tell us how much money we would take in at the cash register for selling 12 units. The profit function is as you might expect. We're just going to subtract the revenue function. We're going to subtract the cost function from the revenue function. It costs us $10 to make 12 units and we sell them for 20. Our profit is $10. So that's the profit function. Finally, we have two more. These are marginal functions, and this is where derivatives come into play. The marginal cost function. This is the function that tells us how much it costs to make one more unit. Like say we've made 300, and we want to find out how much does it cost to make the 301st unit, and that's what this function will tell us. And it's the derivative of the cost function. Now, just to know, costs aren't the same for each additional unit made. If we have a factory and we're making things, that factory has a fixed overhead. So the more things we make, the lower the cost per thing is, because we're not paying more for the factory. It just costs the same whether we make 0 or 5,000 units. So that's why we have a marginal cost function. Then the marginal profit function tells us how much profit we make for selling one more item. And since cost varies and since revenue varies, the profit will also vary. It's not straight up. We don't make $2 profit for every item starting from 1 to 500 items. It's a changing situation. So that's why we have these two marginal cost and marginal profit functions. These are derivatives of the cost and of the profit function. Now that makes sense because the marginal is how much for each additional. It's a derivative. So it's a slope of a tangent line to, for example, the cost function or the profit function. So the slope of the tangent line is the rate at that point, which is in economics term, that's the marginal cost or the marginal profit. So this is where derivatives come into play in a very real way in the real world. So let's go ahead and do our example problem. We have this company and they estimate the cost for making X number of items with this function, 100 plus X minus 0.01X squared plus 0.00006X to the third. So that's our cost function. Their estimate of their revenue comes from the revenue function, 22.8x minus 0.001x squared. So now we have two functions and we can figure out our profit function if we need to, but we're going to do something else first. What I want you to do is pause the video and find out how much does it cost to make 300 items. So that would be C of 300. Okay, straight up plug and chug question. I did my cost of 300, so I put 300 into my cost function. Here's my plug-in step, worked that on the calculator. I got 1,120, and we're dealing in euros in this example. I didn't put that in there, but we're dealing in euros. So, next prompt. Find the marginal cost for the 301st item. So we want to know how much it costs to make that one more item. So take a look. We need to figure out what the marginal cost function is and then put 301 in there. Now I'm going to leave you to do that. Okay, here we go. So I went ahead and found the derivative of my cost function there. I get 1 minus 0.02x plus 0.00018x squared. So that's my marginal cost function. Then it's a plug and chug. I'm just going to put 301 into that function. Here's my plug-in step, do my calculation, and I get 11.2 euros. Next prompt, find the marginal profit for selling that 301st item. So what we're going to need to do is get the marginal profit function. That's P prime of X. I see two ways to do that. You could figure out the straight up profit function from over here, just combining the revenue and the cost functions. That would give you the straight up profit function, and then take the derivative of that for the marginal profit function. That would work. You could also, we already have our derivative of our cost function. We could take the derivative of the revenue function and then subtract the derivative of the cost from the derivative of the revenue, and that would also give us the marginal profit function, which indeed is the route that I'm going to take in a minute, but I'd like you to pause the video and do that yourself. Okay, let's see how you did. So I went ahead and put the derivative of my revenue function, which is the derivative of this guy here, I put that there, and I'm subtracting the derivative of my cost function. I use my parentheses because I got to keep track of my signs because I have a minus out there. It might get a little tricky. So I ended up with this function. That would be my marginal profit function. When I put 301 in there, I get out 11 euros. Okay, let's move on to a science example. So check this one out. It's temperature of pond water, there's water in some pond somewhere, is given by this function. Capital T, which is temperature in degrees Celsius, of n, which is our number of days, is 18 plus 12 times n times e to the minus n over 3. So somewhat of a complicated function. We're going to be able to take the derivative of that, no problem. So here's our first problem. Find the average rate of change in temperature in the first 18 days. So what's the average rate of change? That's just going to be the total change in 18 days divided by 18. So all you're really going to need to do is be able to calculate the temperature at the start and the temperature in 18 days. So go ahead, do that, and come on back. Okay, so I just plugged in temperature of T0. That's our initial state. We haven't had any days go by. That's just going to be 18 because this whole term here is going to go to 0 because there's a 0 right there for n. Doesn't matter what else is going on. So it's just going to be 18. So that's T of 0. T of 18, I went ahead and did my plug-in step with my n's where I need them to be. Pulled out my calculator. This gives me 18.5. So ending temperature, starting temperature divided by number of days. That's 0.0297. Stop for a minute and think, what are the units of this number? Degrees per day. Degrees per day. Especially with a science example, you want to circle back around to your units to be able to say what they are. Okay, so that was the average rate of change over an 18-day period. Now, it might be useful to figure out the rate of change at any point in that 18-day period. So that's where the derivative of this function comes in. That'll give us the instantaneous rate of change at any point in time. So I want you to pause the video and find T prime of n. So to do the derivative of this function, a couple things to notice. First off, this goes away. Okay, so normally we would take the derivative of this and we'd add it to the derivative of that, but we don't. That goes away. So all we really need is the derivative of 12n e to the minus n over 3. And it's actually not as bad as you might think. What we have is a product rule. We have 12n times e to the negative n over 3. So we have a product rule, and then this one requires a chain rule to find the derivative. So I went ahead and did my u, which is 12n, my u prime, which is just 12, my v, which is just e to the minus n over 3, and then my v prime, I just did the chain rule, so there's a minus 1/3 times n in the exponent there, so the minus 1/3 comes out, and I just leave my exponent the same because we're doing e, so the v prime is minus 1/3 e to the minus n over 3. Whew! Okay, product rule just means I do u prime times v plus u times v prime, which is indeed what I did here in this step. Here's my first two, my u prime times v, and here's my v prime times u, and then it's just a little bit of simplification. I can't really do a whole lot with that. That's 12e to the minus n over 3, and then this is, I've got a 12 here, and I've got a minus 1/3, so that makes that a minus 4e to the minus n over 3. So there is my t prime of n. Woohoo! One last calculation and we'll be done. So check this one out. I went ahead and copied our derivative function up here for you, and I have to own up. I left the n out of that term on the last board. So it's supposed to ride along in there, and I just left it out. So there should be an n there. So that's 4 times n times e to the minus n over 3. So just fix your notes on that because that is part of our derivative function. So moving along, find the exact value of the instantaneous rate on day 18. Now you remember the first one we did, we found the average rate for all 18 days. So this is the rate of change on day 18. It's gonna be different than that number. So go ahead, pause the video. This is straight up plug and chug. You put 18 into our derivative function, calculate it on down, come back when you have an answer. Okay, let's see how you did. Here's my plug-in step. I'm just putting in 18 for n. So that takes, up here we have minus 18 over 3 is minus 6. And then I remember to put my 18 for that n, and then my 18 up here in my exponential portion of my function. This reduces down to 60 e to the minus 6th, which is minus 0.149 degrees Celsius per day. Now, if you recall, our average rate of change was 0.0297 degrees per day. So it's increasing faster and faster. So this pond is probably moving into winter where it's getting colder and colder and colder, and it's getting colder at a quicker rate. Okay, apologies, I lied. There is one more example, and it's important. This is a physics example, and we need to do these types of problems. Our textbook calls them kinematics, same thing, physics, and certainly if you're in the IB, you're gonna see these on your test, and pretty much in any class on calculus, physics is like one of the primary places where we do calculus. In fact, it's one of the places that helped give rise to calculus. So it's all intertwined. So before we jump into this problem, I want to do a quick little review of how position, velocity, and acceleration are related through calculus. So right over here, I've got our 3 main functions. Position as a function of time, that's s of t. Velocity as a function of time, which is v of t. And finally, acceleration as a function of time, which is a of t. Now, these 3 functions are totally related to each other. If you have the position function, take the derivative of that, and you have the velocity function. If you have velocity and you want to know what acceleration is, you take the derivative of that, and you end up with the acceleration function. So all you need is one of these, and you can get easily to any of the other ones, because the other half is, if you have the acceleration function, you just take the integral of that, and you end up with the velocity function. Same thing with velocity to position. Just take the integral and you get to position. Now this makes sense because integration and derivation are inverse functions, so you're going up and down through the same, basically the same process, just like multiplication and division are inverse processes. So we're going to use a little bit of this knowledge in this example. So let's get started. Here's what we've got. We've got a diver. Diver problems are a classic physics problem. Jumping off a cliff, we can ask all kinds of questions about what's happening. So this diver jumps off a platform at t equals 0 seconds. That's the start of this little mini experiment. The height above the water in meters is given by s of t equals minus 4.9 t squared plus 4.9 t plus 10. Notice how height above water, that's position. So we're in the position function, that's what this is. Your other clue is they're using s of t. So generally speaking, certainly if you're in our textbook, probably anywhere in the IB, if you see an s of t in a physics problem, you're looking at position. So here is the position of the diver as a function of time as soon as they jump off the platform and start heading down towards the water. Okay, first prompt, find the average velocity during the dive. Now, you might get just that. And there's a little bit of thinking involved in figuring this one out. So I want to get you started. First off, the average is going to be the total distance over the total time. So there's a couple things that we can get easy, or one in particular. How high above the water is the diver at the beginning? That's t equals 0. We're actually even told that. So at the beginning, the diver, you put zero in for t to find the height. And we know, okay, so that term goes to 0 because t is there, and this term goes to 0. So the diver is just 10 meters above the water, so the diver is going to travel 10 meters till he gets to the water. So we know the total distance on the top is going to be 10. Now the bottom is a little different. We're going to have total time is going to be the amount of time from when they start to when they hit the ground. So the time at when they hit the ground, that time we can call it T1 minus 0 is going to be our time. So now we need to do a little bit of math to figure out what that time is. So I want you to pause the video and think about that for a minute and come on back. Okay, so the main critical thinking step is to realize when the diver hits the water, the height is 0. So what we have to do is we have to set our height function equal to 0 and solve for t. So here we go. I said s of t equals 0. That's the general case here. Now I put my function in there. That's the s of t. We don't know what t is. We know the whole thing equals 0. So from this point, you can do quadratic formula. Some calculators just let you put that right in there and get your result. Some calculators have this little solver deal that will also do that. This is going to generate a negative answer also. Throw that away. We're not interested in the time before the diver jumped. So really the only answer is this one. T equals 2.01354 seconds. Now, quick word of advice. Carry a bunch of decimals along here. Sometimes our answer is going to, the extra decimals have a large influence on the ultimate answer. So in these problems, it's a good idea to carry a bunch of decimals. So here's what happens, is this becomes 10 over 2.01354 seconds. So it's 10 meters over that seconds. So go ahead, pause the video, do that calculation, come on back. Okay, so when I do the math on that, I get minus 4.79 meters per second. First question, actually let's do the second question first. This can also be written as minus 4.79 ms to the minus 1. So as you recall your exponents, ms to the minus 1 is really m over s, which is what this is. I don't really care for this notation myself because this makes intuitive sense. Meters per second. In common language and common places, that's how we talk about rates, something per something. Well, this is mathematically correct and perhaps more precise. Actually, I don't even think it's more precise. It's just different. But it just doesn't make as much obvious sense what we mean when we say ms to the negative 1. Okay, so here we are. We know that this rate is minus 4.79 meters per second. Why is that negative? It's not like an accident that comes in negative and we just ignore it and we say the rate is 4.79 meters per second. Why is that negative? Think about that for a minute. Okay, if you realize it's because we're going down, you're right. On the coordinate plane, down is negative. So we have a rate that's going down. This is like a negative slope. You can see it sort of that way. So our rate is negative. So it asked for velocity. And you remember, velocity has direction in it. Technically, velocity is speed plus direction. And so that's why velocity has a negative. Now, you might get a tricky test that now would say, what's the speed of the diver? And you might be going, well, I thought I just calculated velocity. And you did, but you didn't do speed. So if it asked you for the speed, you just tick off the negative and just say 4.79 meters per second, because speed does not have direction. Velocity does. Question number 2. Find the instantaneous velocity of the diver when she hits the water. So there's a big clue in what to do. Whenever you see instantaneous, you should start thinking derivative. Okay, because a derivative function gives you the rate of change at a point. It's not an average rate of change over a period of time. It's that rate of change right at a point. It's the slope of a tangent line. That line is tangent to the function at a point, and it represents the rate of change at that point. So this problem is asking you or requires you to figure out the derivative of the position function, which would give us the velocity function, and then use that function to find out the rate of speed, the rate of velocity at the moment that the diver hits the water. We already know that time. We know what that was. We got that from the last board. So we'll plug that in. But first step is just simply take the derivative of our position function and come on back. Okay, I went ahead and finished that one up. First off, the derivative of the position function, I'm writing s prime of t, but I could write v of t because that is s prime of t. So anyway, the velocity function is minus 9.8t plus 4.9. That's just the derivative of that function. Now what we do is we take that time. Remember in the last one, we set the function equal to 0 to find the time when the diver hits the water. And that time was at 2.0135 seconds. So now we do s prime of that time, plug in step here, work it through, and I get minus 14.8 meters per second. So going pretty fast. Just in 10 meters of falling, we're going pretty fast there. I just want to make one more point. If we were talking about this diver and wanted to give one significant piece of information about her speed, this one, not that significant. The diver fell over a period of 2 seconds, and the average speed over that period of time was just about 5 meters per second. Not as interesting as the fact that when she hit the water, she was going almost 15 meters per second. That's, I think, much more interesting and much more relevant to the whole situation that we have here. Now that you've watched the video, take a moment and write down any questions that you might have so you can bring them to our next class. Remember that you can always watch the video again and perfect your notes. Finally, if you enjoyed the video, please click the like button down below. And if you'd like to help me grow my YouTube channel, please click subscribe.